Hey RubyConf, my name is Ariel Caplan, and I'm here today to open your eyes to some powerful secrets of Ruby hashes. Now, however long you've been programming with Ruby, you've for sure come into contact with a hash, and you probably think of it as being somewhat analogous to a pocket knife. It's a really good tool that has a particular use, and it does that one thing and it's good at it. In reality, hashes in Ruby are more like a Swiss Army knife. They can do a whole lot of different things and actually be quite good at a good number of them. In order to explain what I mean, I'm going to have to talk to you a little bit about life. Now, when I say life, I don't really mean the concept of life. I'm talking about John Conway's Game of Life. Now, this is a game that's mostly interesting for mathematical purposes, but over time became of great interest to programmers as well, because it's a game with a few simple rules that lets you, if you want to learn a new language or a new framework or something like that, you can try to program this game of life. You can implement its few simple rules, and you can learn a lot about what that language has to offer. So let's dive into what this game is, and then we'll see how it relates to the topic of the talk. So the idea is that you divide the world into a big, basically an infinite grid of squares, and each square is assigned an initial state of being alive or dead. In this case, we've marked the alive squares in blue, and the dead squares have remained empty white. Now, that's our initial state. We then have to calculate the next step. And so for each cell, we look at the cell itself and those around it, and based on a few simple rules, decide whether it's going to be alive or dead in the next round. So if the cell is currently alive, we see how many live neighbors does it have right now. If it's 2 or 3, it will continue to live, otherwise it will die off. And if the cell is currently dead, then it will remain dead unless it has exactly 3 live neighbors, in which case it will be spawned into a new cell. So just a couple of examples. The cell on the bottom left that's currently circled in green, hopefully you can see that. It has exactly 1 live neighbor, and that's not enough, so it's going to die off. The cell on the top left is surrounded by 2 live neighbors, and because the cell itself is alive, then that's great. It will continue to persist in the next round. This cell on the bottom right has also 2 live neighbors, but because the cell itself is dead, that's not enough. It needs 3. So it's going to continue to be dead. But the cell on the top right has exactly 3 live neighbors, and so even though it's dead right now, next round it's going to be alive. And so if we do this calculation for all of the cells in our system, we get to a formation like this. One more generation, we move here, another step we go here, another step we go here. And if you're paying attention, you might notice that now we're exactly where we started, right? We started here, and we ended up here. Now, I wrote 2 different implementations of John Conway's Game of Life in Ruby, and you're going to see there's a slight difference between them. Okay, they're almost exactly the same. It's the same logic, the same algorithm, but again, a slight difference between them. So we have a bunch of what we call gliders. That's this formation that I showed you, and on the left you can see they're moving along quite nicely. I made it a looping world so that when it goes off the bottom, it comes back on top. Same thing for right and left. On the right side, you can see it's a little bit slow. We got through about 5 steps, and then just the algorithm got too slow to be able to move forward in real time. And actually, the algorithm on the left, it actually would be faster, but I slowed it down with some sleeps so that you could see the gliders moving along nicely. Now, the difference between the left and the right side is one simple thing. The one on the left makes good use of hashes, and the one on the right does not. So more on that later, but first let me talk to you a little bit about myself. So hi everyone, again, I'm Ariel Caplan. I've been a Ruby programmer since I graduated the Flatiron School in 2014. I currently work as a backend developer at Cloudinary. This is not my first Ruby job. Actually, I've been working a number of Ruby jobs along the way, which has been a lot of fun. And at Cloudinary, I'm working on one of the world's biggest Ruby applications. It deals with billions, that's billions with a B, of requests for images and videos every day. Basically, if you have anything in your application, if you're online and you use images and videos, we probably have some cool things we can help you do, including just optimizing your websites for display on mobile, faster load time, stuff like that. You can find me online at AM Caplan, everywhere that matters, so go ahead and tweet at me. This is pre-recorded, so I will be happy to respond to your tweets during this talk, but again, there'll be a Q&A later, so you don't have to tweet at me right now. And of course, amkaplan.ninja, you can find the slides for this talk if you want to follow along yourself. All right, let's get down to basics. So what is a hash? At least the Ruby edition of a hash. So a hash is a performant key-value pair store. Each word there is really important. So store, right? It's a data store. It stores pairs of keys and values. So you set things and get things based on keys. And it's performant. What that means is however many keys and values are inside of your hash, doesn't matter if there's 3 or 30 million, it'll take the same amount of time to get and set a key-value pair. Now, importantly, and this is fairly unique to Ruby, I've looked at a number of other languages and I couldn't find anything else that has this property. Keys can be any Ruby object, values of course as well. So they can be, not just symbols and strings, but also numbers. They can be active record objects. They can be whatever random standard library class you feel like putting in there. Doesn't mean that you should, but fundamentally you can. Now, to create a hash, you can use literal syntax, which uses curly braces, and then you just put in the contents of the hash on the inside. Or you can use a more explicit syntax where you use the hash.new method, and we'll see in a minute why you might want to do that. And then you can go ahead and set your keys and values afterwards. Now, there are multiple ways to fetch out of a hash. So you can use hash.fetch, which is going to raise an error if that key is not part of your hash. That's a more strict version of fetching, but you can also have a more easygoing way of fetching. Now, some people think that this is just totally lenient, and the idea of square brackets is that if it's there, then I'll get the value. If not, then I'll just get nil. And that's actually not true. It's actually just fetching with the default value. So it's saying if the key is there, get me the value. If not, get me the hash's default value. And the default value is nil. But you can choose your own default value. So if I want to create a hash where the default value is the number 4, I can do that. I just pass 4 as an argument to hash.new, and I will get a hash with a default value of 4. More on default values in a little bit, but first I want to say a little bit more about the fact that any object can be a key. So we're going to look at a couple of standard library classes that use hashes as we go through this talk. The first one we're going to look at is set, because I think it's a really good example of the power of letting any Ruby object be a hash key and why that makes any sense. So set is part of Ruby standard library. It's not, you don't require any gems or anything, but you still have to require it because it's in the standard library. You can then call set.new, create a new set. There are different ways to create a set. We're not going to get into that right now, but you can create a set and pass in an array. And each element of the array will become an element in the set. You can then ask the set, do you include this element or not? If it includes it, it will say true. If it does not include it, it will say false. And the important thing to realize about this include is it's actually, it doesn't matter how many items you have in your set. You could have tens of millions of items. It will be just as fast as if you had 1 or 2 items in your set. It's very, very performant. And we'll see why in just a sec. Okay, now you can add an item to your set, but if you add an item that's already there, it's not going to really do anything, right? So however many times you add 3 to your set, it's just going to have 1 3 in it. So these are the 2 properties of a set. Again, the include operation is really fast, and it will only add 1 of any item, and that's why it's called a set, right? Because it's every item in it is unique. Now let's look at the implementation to understand these properties a little bit better. It actually turns out you could go ahead and open up the standard library code, and you'd probably understand it. It's fairly simple in terms of its implementation. So when we create a new set, we initialize with an enum. That just basically means something that's enumerable, like an array. And we create an internal @hash. This instance variable is set to a new hash with a default value of false. We then merge in our array, which just means iterating over our array and doing the add operation. And all add does is it sets a key value pair inside of our hash. So whatever object we're adding is going to be set as the key, and the corresponding value will be the Boolean value true. And when we call include, we're just doing a bracket access on the hash. So we're saying, is this object included in the hash or not? And if it's included, well, remember how the value we set above is true, so it'll be true. But there's that default value, false. So if the object is not there, it's just going to return the default value, which is false. But if it's there, well, it's going to return true. So really, really a simple concept, a very simple implementation, but a really powerful class that is really useful when you have, it happens very often, you have a list of items, a standard list of items that's maybe even like a property of a class, and you often need to check, is some user input included in this list? And set is a much more performant way of accomplishing that task versus an array where you have to search through every element and compare it to whatever is the input. Now let's get to a very practical example of how you would use set, and I'm just going to talk about set, but theoretically a hash would make sense in certain variations of these same circumstances. So at my first job, I worked at a company where one of our products was the ability to search for a healthcare provider. And when you get your search results back, there are certain disclaimers that we might want to display depending on the results of your search. So, for example, we might have a disclaimer that if any of the providers are in network tier A, whatever that means, then we should display some disclaimer text saying, oh, you should really choose that provider because you'll get lower out-of-pocket costs. So the disclaimers look like this. They had key, value, and some kind of text. And then the providers had metadata, which included all sorts of information that we might want to use to decide to display a disclaimer. So how are we going to, given a list of providers, figure out which disclaimers to show? So this is the code that somebody wrote, basically saying, let's iterate through all the disclaimers. Let's find the ones for which there's any provider that has this key and this value, right? Looking up inside of the metadata hash, this key, seeing if it's equal to the value. Now the problem with this code is it's not very performant. So let's say we're going to run this outer loop once per disclaimer. There's 300 disclaimers. And then for every disclaimer, we're going to run through every last provider. So that's 500 different providers in our search results. So that comes out to 150,000 operations. And you'll say, oh, that's just the worst case. But actually, we displayed almost none of the disclaimers, right? Maybe 3 disclaimers for a search. So actually, we would usually make it through all those 500 providers and not find a match. So yeah, 150,000 operations really was not very performant. It was taking a long time. What I suggested was let's switch it over to something like this. So we create a set of provider data. And for each key value pair in the provider metadata, we're just going to add on a new hash which has the key and value in that provider data. And of course, if multiple providers have the same key value pairs, that's great. The set will just, it'll only add one of that key and value, regardless of how many times you add it into the set. Then we're going to iterate once over all the disclaimers, and for each disclaimer, okay, this is a key value pair that you're looking for. Great, let's see if that's inside of our provider data set. And that's 500 operations for each provider, 300 operations for each disclaimer. It comes out to about 800 operations, and that's it, right? Compare with 150,000 operations, right? You do something 800 times, you may or may not be okay, depending on how expensive it is, but 150,000 times, right? That's really bad. So this was a much more performant way of accomplishing the same task. One little warning about hash keys and trying to use all kinds of different keys in your hashes. Make sure that they're simple objects. Don't use anything that's complicated. So strings, symbols, numeric types are usually fine. Some reservations about floats, but definitely integers are fine. And note that floats and integers that are the same number won't be equal. So be really careful around floats, but integers are fine. And arrays and hashes of what we would call the valid types, right, like string and symbol. So all those are totally fine to use as hash keys. In my experience, in my small amount of experimentation, they seemed reasonably performant. But if there's anything where equality is not obvious, like don't use active record objects inside of your hashes as keys. You're going to end up having problems and bugs and things that are hard to track down. Just don't do it. Okay, now let's move on to talking a little bit about default values, right? We talked a little bit about object keys, and now we're going to talk about default values, and we're going to see some things that look almost like magic. So default values. A default value for a hash is one object that will always be returned if the key was not found. Note that it does not set a key value pair. So if I have a default value, I ask the hash with square brackets for one of its keys. It doesn't find the key, so it returns the default value. I don't now have that key value pair inside of my hash. It's not impacting the original hash. You can set it, this default value, at hash initialization time, or later on you can just call .default equals, and that will set the default value just as well. Now, one important caveat, it will always be the same object. There's no duping or cloning or anything happening. It's just the same object. And so if you create a hash with a default value that's mutable, it can change, like a string. So in this case, we create it with the string ABC. And then we say, OK, let's pull out the default value. We're going to ask for a key that's not there. We're going to get that default value back. We then modify that string. We add on the letter D to the end of the string. And what's going to happen is now when we ask the hash for another key, we can see the original default value object has been modified. So be really careful when you use default values. The best thing to do is to use something like a symbol or a numeric type, which is not, it cannot be changed. If you don't, if that's not relevant, then maybe consider freezing the string, or maybe a hash or an array or whatever it is that you're using that can be changed. Freeze it when you put it in to avoid bugs down the line, because those are very hard to track down, I can guarantee you that. Okay, now default proc. So we didn't talk about this yet, but default proc is kind of like default value, but instead of being a value, it's a proc. It's a function that will be run when a key is not found. And unlike default value, you can decide, yes, I'm going to set this key value pair if the default proc is run. Now the default proc, you can set it at hash initialization. However you're going to set it, the proc itself takes two arguments, which is h and k. Traditionally, it's the hash and then the key that you've just asked for. And if you want, you can preface whatever you're going to write. You can preface the return value of your block with h, k in square brackets equals. And so you're going to set that key inside of the hash, not just return a value, but also set that key value pair. If you don't want to do that, that's fine too. You can just have have the block return some value and never set a key, and that's fine too, depending on your use case. Now, if you set it after hash initialization, this is how it looks. You just call hash.defaultProc equals, and then you give it a lambda, and give it a proc. Either way, it's the same. I just happen to like lambda syntax, so that's why I used it. One really cool tip I picked up from Optigrim is that default proc can reference itself. So if you set your default proc to a local variable, you can have the default proc itself reference that variable, and have this arbitrarily nested hash structure. So in this case, again, default proc equals, right? Ultimately, we're saying that we're lazily setting this key value pair to have the value of a new hash with the same default proc. So when we access, in the second to last line, hash square brackets symbol A, we get back a new hash that has that default proc. And then when we access on that square brackets B, we get a new hash that has that default proc. And then when we set C equals, we're just going to set something inside of that hash. And so we get this nested hash structure basically without ever building it up on our own. So, a little bit dangerous in terms of the methodology, but it's interesting to think about what are ways that we could use this practically. Would we want to use this for a configuration object, for things like that? Is it too dangerous? Which it very well might be. But just cool to think about, the power of this default proc. And you might be thinking, well, isn't this kind of recursion? And maybe a little bit, but I want to talk to you about real recursion. So, there's a lot of really cool recursive things you can do with hashes because of this default proc as well. So we're going to talk about the classic example of recursion, which is the Fibonacci sequence. So the Fibonacci sequence is a sequence of numbers where we have the first two numbers are 0 and 1, and then after that, every number is the same as the sum of the two previous numbers. So just taking a random example from the middle, we have 13. That's the sum of the two previous numbers, which are 5 and 8. So that's the definition of a Fibonacci sequence, right? Every number is just the two previous numbers added together. Now here's how you might program it if you wanted to do it in a performant way. You do it iteratively, and I look at this code and you could maybe start to try to reason about it, but it's not very clear exactly what it's doing. Contrast this to the recursive version, which is not very performant for reasons we'll see in one sec, but it's beautiful. It says exactly what a Fibonacci number is, right? If it's 0 or 1, then it's just the number itself. Otherwise, give me the two previous Fibonacci numbers, right? The fib of n minus 2 and the fib of n minus 1, and then just add them together. And so we're effectively describing what we're doing. We're not going down the imperative path. We're talking about almost declarative programming. We're describing what a Fibonacci number is, and the computer goes ahead and figures it out, which is really cool. Now you can do this with a hash also, right? This is the same code. It's just written as a hash with a default proc. So the default proc of the hash is set this key to the values for the two previous keys, right? So we can, inside of our default proc, we can access a value on the hash, and that actually works recursively. If I ask it for the value of 100, it'll ask itself what's the values for 99 and 98. Of course, we have to set our base case as well, so that's why we have hash 0 equals 0, hash 1 equals 1. What's also cool about this is this recursive method can calculate in a second on my computer, my MacBook Pro, the first 35 Fibonacci numbers in about a second. This can calculate the first 100,000 Fibonacci numbers in a second. So 35, 100,000, what's the difference? Well, let's think about it. When I ask for the Fibonacci number 4, it's going to say, okay, break that down to 3 and 2. 2 breaks down to 1 and 0. I know 1 and 0, right? That's our base case. And then it can add them up from there. Well, 3 we have to break down also. That's 2 and 1. 1, again, is a base case, so I know it. But 2 we have to break down into 1 and 0. And then we can, go ahead and add it up again. And I want to point out, yeah, those two are the same pyramid. Or tree. And so we build up these gigantic trees where a lot of the nodes are the same. We're doing the same calculations again and again and again. And compare this with the hash version, which again, hash 4, that breaks down to hash 3, hash 2. Hash 2 is hash 0 and hash 1. 3 is 1 and 2, but I've seen 1 before because that's my base case, and I've seen 2 also because I calculated it before just now. So I don't have to calculate it again because it's been cached inside of my hash. And so, that's the difference in terms of 4, 9 calls versus 7 calls, not a big deal. It gets a little worse when we go to 5. It's 15 versus 9. When we get to 6, it's 25 versus 11 calls. And finally, when we get to 35, so the method version is making almost 30 million calls, 30 million method calls just to calculate this number. For the hash version, we're making 69 calls. So that's pretty nice, right? That's a big difference between those two methods of calculating in terms of how much work we're doing, because we just cache the results along the way. That will all bring us to Conway's game of life. So I made an implementation which completely separates the logic code from the display code. And the display code basically goes through the whole grid, and for each square on the grid at any given step, it says, hey, logic code, here's coordinates on the grid, x and y, and then here's what step I'm on, what generation of the game that I'm on. And the logic code has to give some kind of response. And so if we're on the initial step, we have our initial steps, our initial states that we've set up already. But if we're past that, then we have to look at history. And so we say, okay, well, let's look at what it was last round for the surrounding cells, the neighboring cells, as well as this current cell. And then, the logic of if the cell's alive, then number of live neighbors has to be 2 or 3. If the cell is currently dead, then the number of cells has to be exactly 3. Otherwise, it's going to be dead. So that's the code that you see. I want to show you the same code, but with a little difference, that instead of a method, we're using a hash with a default proc. So I'm going to go back and forth. You can see it's basically the same code, right? Letter for letter, minus the part where this one is asking. It's doing recursive method calls, and this one is doing recursive hash access. And again, this makes it very clear, right, that we're just kind of marking down as we go the results in the hash version, and we're accessing those results. But in the function version, we're recalculating it every time from scratch. And so the results, as we saw before, speak for themselves. Right on the left, it just kind of runs through, goes fast, fast, fast. On the right side, it just kind of dies after a couple of stages. It's on 4 now, it just got to 5. And it's just kind of stalled. But look on the top also, you can see that the hash version, instead of using more CPU, it's using more memory. So the amount of memory is going up and up and up and up as the hash holds more and more information. So that's a trade-off that we make when we use a hash, when we use really any kind of cache. Now, I want to jump into something a little bit more practical, but in order to explain it, I need to talk about one more piece of the standard library, which you may or may not have heard of. I didn't know about it until I was preparing this talk. It's called the Abbrev Library. So the Abbrev Library is pretty simple. It will take an array of strings, and it will tell you what are the unambiguous abbreviations for each of the strings. And so given the two strings conf and code, if I type into my command line cod, it's clear that I'm referring to code, so I can just auto-complete that. But if it's conf, then right, I shouldn't write cod, right? That cod clearly refers to code. So that's the idea of the Abbrev library. It helps us take an abbreviation and figure out what someone's referring to based on a set of options. Now here's the implementation. I'm not going to read through it. I'm just going to explain to you graphically what it does. So we have our table, which is a hash. We also have our scene, which is a hash. That's what they're called in the code. And so we start with a string. The first string in our list is conf. We start with the whole string. We add it to our scene. We mark it down that we've seen it once, right? Scene is keeping track of how many times we've seen something. And since we've only seen it once, we will add it to our table and have that be a key with the value being the current string that we're on, which is conf. The same thing again with con. We add it to our scene. And then we're going to go ahead and add it to our table, again pointing to conf. Keep sorting the strings, co. And again, add it to our table, and C, we're gonna add it to our table as well. Now, we're done with conf, so let's start with code, and again, start with the full string, shortening it as we go. So code, again, adding it to scene, adding it to our table, pointing in this instance to code. Cod, again, pointing to code. Then we get to CO. It's a little bit different, right? Because we've seen it before, so we're gonna increment the number of scenes. We say, oh, we've seen it before, we have to remove it from our table. So we're gonna go ahead and erase it. The same thing is going to happen with C. Okay, increment the number of times we've seen it and erase it from our table. Now we're done, and the table contains exactly the information that we were looking for. Okay, each of the unambiguous abbreviations is associated with what it abbreviates. So here's the condensed version of the code, and I want to just point out a few things. At the top, you see we've defined two hashes. At the bottom, we're returning our table. That's our return value. We're iterating over each portion of each word. And if we've seen an abbreviation just one time, then we're going to add it to our table. If we've seen it more than once, we're going to delete it from our table. So that's exactly what we saw. Note that scene has a default value of 0. And so when we are incrementing values in our scene table, we can just basically act as though it's already set to 0, and we just increment it by 1. We never say, scene square brackets abbrev or equals 0. We don't have to do that because we have a default value. And so this is a pattern that is actually really useful in app code to be able to create counters. So let's talk about some of our application code. This is something that we can do in a lot of places in our real everyday code. So we can create a hash with a default value of 0. Let's call it totals. Let's say we have items from a receipt or an invoice or something that we want to tally up. How many of each do we have? And so we just start incrementing. In the third line, you can see we're incrementing inside of our totals without ever setting any item to 0. We just rely on that default value. And in the last line, this is really cool. We try to access an item that's not there. Let's say there's some code later on downstream that's going to assume that the item is there, but it's not there. We never set it because we didn't see it in the receipt. But it still works because we have a reasonable default of 0. And this can save us from a lot of bugs. Now let's go ahead and move to an example from Cloudinary's code, literally copied and pasted from our code base. So in the first line, you can see we created a totals hash with a default value of 0. Again, one of these counters that works really nicely, as we've seen. The next line is kind of building on that complexity. We have by company, which is a hash with a default proc that lazily generates a hash with a default value. So what's going on there is we're defining the structure of our data, where we want to have a hash where each key is a company name, each value is a hash with all the totals for that company. And so in the case of the totals hash, right, if it just defaults to 0, but in the case of the by company, we actually have the ability to access it by company name, ask for a sum, and even if we have not put in any information about that company, we still know what the shape of the data is supposed to be, and we can have a reasonable default of 0. So this kind of thing can save you a lot of problems in production, where the data might be a little bit different than you expected, but the shape always should be the same. Now here's another thing that you can do that happens all the time, memoization. So memoization, right, the concept, we use it in Ruby all the time. We lazily assign an instance variable to some expensive calculation. We only want to do it once. And that works great if it's just one thing. But what if you want to calculate a few things and they all have the same shape more or less? You might create a few different methods that look the same and just use a different parameter to that calculation, but it's not scalable, it doesn't look very nice, and more importantly, if the arguments are unknown until runtime, this is not going to work. So what can you do? And the answer is a hash with a default value, or rather a default proc, really works very nicely. You memoize a hash with a default proc, where each key is the argument, or perhaps an array of arguments to the calculation. You then go ahead and lazily generate the result of that calculation. And so when you ask the hash for that argument or that set of arguments, it will say, if I've done it already, then great, here's the result. If I haven't done it yet, I'm going to go ahead and do the expensive calculation and then return the result. And this is something that I use literally all the time. So bottom line, what have we covered? We talked about how flexible Ruby hashes are, where any object in Ruby can be a key or a value, and some benefits of that. We talked about how hashes have a lot of dynamicity due to default values and default procs, and that they can be employed effectively to create a lot of resilience in our application to avoid all kinds of errors. We talked about how you can do recursion-like things with hashes that sometimes maybe even work better than regular recursion. And finally, we talked about different caching strategies that we can use, again, taking advantage of the unique properties of Ruby hashes. That's what I have for you today. So thank you so much for listening. I really hope that you learned some new things that you didn't know before. And there will be a Slack chat later, so I would love to hear your questions during that time or anytime over the internet. I'm at AM Caplan. Thanks so much. Have a great rest of the conference, everybody.